Let me introduce you once again, Dr. Stefan Rude. He's, of course, a coordinator at SuT level. And I read about you. Your sweet spot is the interface between engineering and IT. This is where your home base is. And you are an expert on geometric modeling, electrics, electronics quality, and functional integration. And your goal was to develop solutions that are ready to use when SuT level is finished. And I'm now excited to hear more about the toolchains that Frank already introduced to us, toolchains for simulations of autonomous driving. Thank you very much.
Thank you, Laura, for this kind introduction. And good afternoon, ladies and gentlemen, again. From my side now, I'm presenting toolchain issues for simulation of automated driving within the SuT level project, within this project called simulation-based engineering and testing of automated driving. Let me see if it works. Yes. In the scope of the work we have already seen, the toolchain is in the middle of the approach, which is influenced by everything around, by simulation-based engineering tasks and the related simulation targets, by the architecture necessary for the specific simulation target, by the models needed to within the architecture for the system under test and for the system's operational environment, as we call it, and for the process which leads to the necessary elements for simulation, and by the used methods and standards to enable the tools for an IT-based operation, which is already shown as a DevOps approach by the end to make it happen in practice. I will present the basic approach which we used as we started 3.5 years before. I will explain again the matrix core dimensions of configured toolchains, then go into details on tasks, systems under tests, operational environments, which is new for the simulation of automated driving, and very important, and I will explain examples we developed to demonstrate the approach. Architectural considerations are shown to explain differences and commonalities of the different demonstrators, and last but not least, I will highlight the benefits and explain the takeaways. So the original basic approach is already a multi-pillar approach, which consists of different test instances. The simulation-based ones like criticality and effectiveness analysis, for example, based on the open path implementation, simulation-based MIL, SIL, or other simulations for automated driving functions, but also for components like sensors, HIL-based testing, hardware in the loop-based testing, and also driver in the loop, or testing test vehicles on a proving ground or even on public roads. All the results of the different test instances must be integrated in a way that in the end, a summary for the purpose of homologation or system release or component release is possible. For input, there's a test strategy necessary with a test concept which must be based on the requirements for a future product. Requirements are to be described as test cases, as a starting point for the multi-pillar approach. In our case, test cases are scenario-based ones and used for the relevant and required and use the relevant and required models. These are preferably standard-based, preferably based on the functional mockup interface, and the assembly of components eventually also standard-based on the SSP, for example, the system structure and parameterization. And for scenario data, we have the standards in the ASAM association, which we have been used and further developed and substantially influenced by members of the SuT level project. mainly ASAM Open Scenario, Open Drive, and ASAM OC. The scope of the SuT level project addressed the horizontal integration of all these aspects for the subset of simulation, and can be used as an input also for the hardware-based test instances, but they obviously use other elements, hardware-based ones, components or vehicles, which we had not in the scope of our project. And within that, for the purpose of traceability, which links test cases with scenarios, with required models, tool chains, and generated results, therefore also data management as a part of a tool chain was in the scope of SuT level. The basic matrix approach you already have seen in the presentation of Frank Köster a minute before. The columns you see the fundamental engineering tasks like analysis, optimization, and testing. And from the left-hand side, the data and scenarios come in, and on the right-hand side, the resulting release, and therefore the necessary matrix and KPIs come out. The elements in the lines, which are related to their operational environment, can be components, subsystems, vehicle system, or even a traffic system. And the basic approach is influenced by architecture, simulation targets, processes, methods, models, and standards, as we have seen it already. What we have done is to prove the concept with some demonstration based on different tool chains, which belong to simulation use cases. There is a traffic simulation called Simulation Use Case 1. There is an example with multiple demonstrators, which is called Simulation Use Case 2. And this is dealing with a closed loop simulation of automatic driving functions. And the third one is an open loop testing of components like sensors, which are camera, LiDAR, and radar in our case, called Simulation Use Case number 3. Those are working areas. To go deeper into the 3 areas as we have seen it is simulation tasks on the top side, into the systems under test, and into the operational environment. It is a basic concept that simulation tasks start with analysis cases, optimization cases, or test cases. In our case, the cases are based on scenarios, as I said. The SuT level project based on some reference scenarios, which contain parameters on various levels, and those parameters can be varied to support the need of huge amount of the required test kilometers, which are necessary to prove the safe functionality of an automated driving function. At the end, the simulation task also has to define the expected metrics or KPIs, so the key performance indicators. And like in classical test management, where you start to define the preconditions, the actions, and the expected results here in terms of metrics and KPIs, are usually also specified in classical test cases. The system under test, on the lower right side of the figure, is a functional model of the automated driving function, which starts from the left-hand side with some sensors like camera, LiDAR, and radar. Also inertial sensors like GPS or wheel speed sensors are used. Then the kernel of an automated driving function starts with sensor fusion through motion planning and motion control to actor management, which goes down to the acting elements like powertrain, steering, and braking. They lead to an update of the vehicle model in its operational environment, and this is a basis for the term closed loop, but this requires an operational environment in which it happens. So on the lower left side is where the input for the system under test comes from, and where the output leads to an update of the system under test, the functional model behind, within the operational environment. This can be very different dependent from the simulation task and target, and dependent from the models to be analyzed, optimized, or tested, as I already said. It can run in a real environment based on real data in the lower left corner of the figure, called reprocessing, as also Nikolai mentioned before, which could be labeled or also described as a model of the environment, which is called ground truth. And based on the ground truth, scenarios can be specified which reference to traffic spaces, which reference to a system under test. And in the scenarios, there are also included the operational design domains, the ODDs. So the scenarios, the ODDs must be represented. In the scenarios, the ODD must be represented. And this is a translation step from the ODD, which must be already specified within the requirements for future products like an automated driving car. Scenarios can not only be based on real data, they can also be created synthetically, and they can be used to deliver the input which is required to an object-based sensor view to the right-hand side to analyze, optimize, or to test an automated driving subsystem. It can also be that scenarios generate pixel arrays. Here for needed piece of software is called ray tracing, and so you can generate also the input for the so-called reflection-based sensor models, or you are using here also real data which shows this S-type curve, which can be also use the material from the real data as from the very beginning. In the next slide, detailing the lower right part of the figure before, the working area on systems under test, we have specified in set level open source models, which can be used free and frankly from the project partners in our demonstrators. Within our simulation use cases, we have a set level project, different sensor models from TU Darmstadt and from Bosch. We have a driver model from the RWTH Aachen. We have a pedestrian model from BMW. We have an open source interface for an automated driving function, the HAT function, highly automated driving function, from the FZI in Karlsruhe, and motion control and vehicle systems and vehicle dynamics from Fraunhofer in Darmstadt. So based on these elements, we are able to build a more complex system, which can be used in simulation use case 1, for example, within a closed loop traffic simulation, and could analyze the criticality of an automated driving function. Simulation use case 2 concentrated on the HAT system functional chain itself. The integration of the function is a closed loop environment, was that we worked on, in fact, this is a subsystem of a total vehicle and can also be used to deal with malfunctions, that means fault injections, and how the automated driving system safely reacts. And the third, finally, in simulation use case 3, we have concentrated on single sensor models for the purpose of an open loop simulation of components. Finally, it is important to say that all open source models are made available for public use in other projects and so on within the automation, solution centered for simulation called ASAS after the SuT level project. Second part is to have a deeper view towards the operational environment. This is the lower left corner of the overview figure, the S-type curve in this overview, the working area on operational environments. As I said already, there are different possibilities based on real data. The model of real data can be used as a so-called ground truth. And this is now specified in the ASAM Open Simulation Interface as OSI ground truth. OSI ground truth can be used to deliver necessary input for simulators. Open Scenario and Open Drive are standards to describe scenarios itself, and traffic spaces. Both of them can use OSI, for example, to create traffic commands, to make an ego vehicle moving, or to make other objects moving, like cars, other cars, or pedestrians, or cyclists, or whatever elements also happen in urban environments and so on. The result from the simulated change of the system under test updates the ground truth in the operational environment, vice versa by the OSI traffic update. The highest level is to create a sensor-specific view on the ground truth, which is called OSI sensor view. And based on OSI sensor view, the output of reflected-based sensor models lead to standardized OSI sensor data. And this is based on ISO 23150 and therefore also related to other ISO standards. All mentioned standards here can be used after the SuT level project because they are hosted, distributed, and eventually further improved by the ASAM Association. So, based on a video, we can see the use of standards based on OSI traffic command, make pedestrians moving, or eventually make other cars moving. The scenery is based on an open drive-based crossing and makes an ego vehicle turn right based on an open scenario file. Here in the video it is shown only a trajectory-based example to highlight in principle the main use of standards in our SuT level project. Open Drive, for example, was substantially expanded by elements which are needed for urban traffic, like signs, signals, or pedestrian pathways, for example. The third part of the three working areas, the upper part of the overview figure on working areas is the simulation task itself. As I explained some minutes before, is a part of the product development process. It is called simulation-based decision process, and it can be an analysis case or an optimization case or a test case again. As a starting point, we need an analysis of the engineering task based on requirements. The test cases must be specified and modeled, and the expected results must also be described and modeled in terms of evaluation modules to prepare decisions. So this is called the first level of the simulation-based decision process. Based on the engineering task, SuT level has further elaborated the credible simulation process, where we go from the analysis of the simulation task, objectives to simulation requirements, to design specifications, implementations, executions, evaluations, and deliver results to the decision process. And as I said before, for different simulation tasks, there are different models necessary, so a process to integrate the right models for the system under test for the specific simulation task is done by the credible modeling process at the lower level. And those process-related results of the SuT level project can be later found and maintained and eventually improved again by the so-called Smart SE project within the ProStep EFIP Association. We learned a lot by the demonstrators of the simulation use cases. We learned a lot in simulation use case 1 as an analysis example, from simulation use case 2 as a closed loop test, and from simulation use case 3 with an open loop test of components, as we already have seen. And here in the application and demonstration of the usability of standard was performed by SAT level and substantially improved, and augmentations of standards have been initialized by SAT level members. The architecture and interfaces are different, dependent from the simulation task, but a general approach based on standardized interfaces has been found. The architecture from each simulation use case and from each demonstrator was and is still to some extent different, but we recognized similarities, which in terms of several iteration steps and lessons learned have led to a possible platform architecture in the middle. And on the top level, we also discussed and synchronized with the ASAM working groups on open standards, the open analysis and testing architecture, which contains, again, the multi-pillar approach in a way that also hardware-based tests, hill or testing on a proving ground, are foreseen. And this is a whole story. As simulation-based engineering tasks can now easily be performed by modular building blocks, which we have within this architecture approach. The subset of the needed elements for simulation are in the platform level as an example, but to say it clear and precise, as an example platform architecture, so the detailing according to the test strategy towards simulation in terms of interfaces and standards was done on the platform level, and the simulation use case itself and demonstrators have been detailed, adapted to the specific simulation task. But last but not least, as a summary, there has been providing a technical basis for scenario-based and modular built simulations of automated driving functions and sensor models. Therefore, we have developed improved IT standards. Demonstrators are used to improve mainly the ASAM standards, and the use of Modelica standards as FMI and SSP was intensively trained in the project. This gave a special drive for the architecture of tool chains, also from the DSpace, IPG and other IT vendors in the project, and from the open source tool chains we have used like OpenPath and Kala. And ASAM standards are cited, that means referenced by some ISO standards like the ISO 4804 or as the upcoming ISO 5083, and various other standards like the ISO 3450X series, or the other way around, like OSI is based on standards like ISO 23150. So examples have been elaborated, like scenarios for an automated lane keeping system, the ALKS, and has been licensed and internationally published as an open scenario files, and is already used by the community for the purpose of clear interpretation of related legal requirements. So open scenario and open try files are licensed from SAT level for scenarios on complex crossings, and also used in other projects like VV Methoden from the Pegasus family and from the artificial intelligence family. Open source models are licensed and offered already through the ASCS, as I said. And some tools are open source, like OpenPath from the Eclipse Foundation, for example. And finally, the process descriptions are maintained and further improved by the Smart SE project within the ProStep EFIB Association. And to say it clear and precise, everything can be found and linked, available through our SAT level website. Last slide. Last but not least, we have here some links to the exhibition, to a number of exhibition booths, to a number of virtual exhibition booths, which can be visited interactively and virtually, starting with the next break. And also in parallel to further presentations and after the presentations today. In addition, the exhibition booths are available on our website and can be visited also after this SAT level final event. And as a main exhibition tools for Toolchains, we have the 3 simulation use cases which we recommend. And the necessary input is described in booths on processes and traceability, test descriptions, scenarios, but not last but not least, by the necessary open source model library, which is like sensors, HUD function, vehicle dynamics, and agents. So this is the end of my presentation. Thank you for listening. And it's time now to have eventually some questions and answers to my presentations. Thank you.